Hello everyone, my name is Jaime Montero, and today I will be showing you how can we estimate earthquake occurrences in a synthetic experiment. Seismologists have been developing more and more realistic physics-based models to explain the fault-slip process that occurs in the earthquake sources that generate the seismic events. But when trying to do an estimation or a forecast of future earthquake events, there is a huge difficulty that needs to be overcome. That there is large uncertainty of the current state of stress, velocities, and strength on those faults that are generating the earthquake. And this is not an isolated situation to large tectonic setups, but also something that is relatable to the Groningen gas field case, where we have reactivation of faults due to the extraction of the gas. And we also have there large uncertainties of the current state of stress and velocities that hampered our possibility of producing reliable forecasts. Now, our proposition is let's use data simulation methods to overcome this situation. These are techniques that are widely used in the meteorology and in the oceanography community and consist in producing optimal estimates of those variables that we are simulating for our system by combining the information from the physics-based models that we have developed as a prior, but then also constraining it or having the likelihood coming from our observations to producing a Bayesian approach this posterior. So there are different data simulation methods that we can use for this purpose. In this study, we used the Ensemble Kalman filter because there has been some promising results from previous studies that have been applying it and been able to forecast earthquake sequences, but in the case when we have a slowly accelerated medium and our velocities reach up to micrometers per second. So what we are trying to evaluate in this study is if it's possible to also predict, or more accurately saying, estimate earthquake sequences when we have a model that accelerates faster and we reach meters per second. So the equation for applying this method, that can be regarded as a Monte Carlo implementation of the least square solution of the Bayesian update problem, is shown here. And what we have in the left hand side is a posterior of an ensemble of models that are trying to sample or better represent that state of our system. X, it's called the state vector, and it will contain all the variables that we want to better estimate. For example, in our case, it includes the shear stress and velocities. Now, in the right hand side, we have a first or initial guess that comes from our dynamical model and is our prior of those variables of the state vector. And we're going to improve it by adding up an innovation that it's the difference that we have in those variables that we can actually measure, or that information that is measurements with respect to what our initial guess from our numerical model is telling us, and we weight that difference by considering the uncertainty of both sources of information and trying to propagate the improvement to the locations or the variables that we cannot measure by using the correlations or covariances of the variables that our model calculates. One important assumption of this method is that the distributions are Gaussian, and this will be key when we are discussing our results. So that dynamical model that we're going to use is based on this setup, that it's going to be a horizontal straight fault representing a strike-slip situation where we have two blocks of rock and the contact between them is the seismogenic zone, and we push the lower block. So we are going to model one slice, a 1D model of this setup, and we're going to model it using a finite difference staggered grid model. The uppermost node, it's going to represent this seismogenic zone that will be experiencing the seismic cycle, so stick-slip sequences of interseismic phase, where we are representing that we have asperities that are getting locked and are building a stress and a strain until there is a moment that we overcome the opposition of the friction and then have a slip behavior and liberate all the energy in the way of seismic events in the coseismic phase. So that's when we have the drop. To model this behavior, we use as a boundary condition there the rate and state friction law, and we model the evolution of the variables using the aging law. Now, for the medium that is surrounding the fault, we are going to use the Navier-Stokes to model the behavior, and we're going to assume that we can place a sensor at a distance from the fault and extract information there at a single location for shear stress and also velocity. Now, using that information, we can then constitute our X, that is the state vector having some components that are hidden states where we have not access to place sensors, that it's the shear stress in the fault, the slip rate, and the state theta coming from this law, and then some other values that come from the medium, that it's from where we can actually observe. And the single observations, we have them in the vector y. So, because we have this dynamical model, we can evaluate the performance or the effectivity of our model by trying to see if we can reproduce or try to better estimate a given model that we already have set up previously as the truth. So we first generate one complete sequence of those earthquake events by defining an initial shear stress that we define as 20 megapascals. And then we extract observations from it, trying to mimic the situation that when we have measurements. Then we produce this ensemble of the Ensemble common filter that we have by producing an distribution of different values of shear stress that we guess are close to that truth that we cannot see, and we produce then a Gaussian distribution of values that is, in this case, 3 megapascals away from the actual truth. But we can see that in the distribution we are covering the possibility of having that actual value. Now, we move forward all those models, in this case 50 models, forward in time until a time k where we have access to observation of these ones that we extracted from the truth. And then we try to use these two guesses to see if we can produce a posterior that comes close to that truth. And we do that by using the equation of the Ensemble common filter. So what occurs here is that we have the PDF coming from the posterior, and by combining it with the information from the observation, we get a posterior that gets closer to the truth. Then this optimal estimation, we introduce it again to the model and then move forward in time until the next observation and produce this process until we finish. So first I will be showing you the results of these improvements or the effect of doing this process of assimilation in the medium in those locations where we have observations. So the black line is the truth that we wanted to reproduce. The red dots with error bars are the observations that I have used for the simulation. And then in green we have first the estimate that it's the ensemble mean, the spread of the estimate that is represented by the percentile 16 and 84 and this hatchet green area, and then the individual members are here represented by light green. So here we have the shear stress and here we have the velocities, and then we can see that the estimates are getting really close to the truth and actually getting in synchrony with it, allowing us to actually have a good guess of their quick occurrence. Now, this is just a section in time of 900 to 1000, where we have approximately 6 cycles of 20 years. But when we look at the long run of 1500 years, we can see that the more information that we get allow us to have less error. What you have in the vertical axis is the mean absolute error, so taking the black line and subtracting it from the estimate of the mean. and dividing it by the number of guesses, so all these different points, to see in average how much error we're committing. And we have more or less an error of 1 megapascals for the shear stress and more or less 2 orders of magnitude for the velocity. Now, here is the most interesting part of the results, that is, what happens in those locations where we didn't even have an observation? Do we improve the estimations using the Ensemble Kalman filter and those observations in other locations? And what we see here in these results is that yes, we have a really good improvement. We can see it in 3 different variables: in the shear stress at default, the slip rate, and the state theta. We have first a comparison that we do before the start of the data simulation. That was the time when I was actually having available observations. We see that before, in the 3 variables, the ensemble was really spread and could not resolve quite well the different events. If we would have continued with that tendency or that estimation without caring about observations, we will have these blue results that are not getting any closer to the black line. But by using the data simulation, we get the green results that we see that in the 3 variables, they are in synchrony and are good estimates. If we try to see again the situation in a long run, when comparing the error initially at the 200s versus the error that we have in the future times, we could see the improvement in this normalized mean absolute error. So we see that for the variable of the state theta, we have decreased to 50% of the error that we will commit in the beginning, and then for the shear stress and for the slip rate, we have actually decreased it by 60%. So now, as I explained in the beginning, this method is assuming that the distributions are Gaussian. So when we analyze the places where we have the most difficulties to estimate, we will see a jump in the absolute error, so the difference between the black line and the green line, but also in the standard deviation of our model. And if we try to see what are the PDFs in there, we will see that for the interseismic phase, we will have best phase because we have a Gaussian distribution. But in the coseismic phase, we will have a splitting of the PDF that makes it bimodal. But what is surprising is that even in those situations, our error is below the uncertainty that actually it's part of our filters, like here. So we are actually covering the truth in our estimations, showing that the Ensemble Kalman filter is producing good estimates of earthquake occurrence. So we can conclude that the Ensemble Kalman filter effectively estimates the earthquake occurrences in this perfect model in synthetic experiments when not having a slowly accelerated medium, which is something very interesting to see, and that the information contained in these shear stress observations and velocity observations are very valuable and informative for the system to try to estimate those current states of stress and velocities that are not available for producing the forecast normally.